Welcome back, everyone, to History of Mathematics. We are continuing our work through Chapter 13 of Stuart Hollingdale's book, Makers of Mathematics, discussing the work of D'Alembert and his contemporaries. As the author states, during this stage of the development of mathematics, which corresponds to the years 1750 to 1850, we see a big focus on calculus and its applications. And one of those applications of calculus is differential equations. Now, the textbook has a fairly thorough discussion of something called the vibrating string problem. Now, that's actually a little more complicated than what I want to get into this video. The situation they're discussing there is you have a string, you pluck the string, and if you know the initial position of the string and how the various forces are acting on the string, can you predict the position of the string at any given time t? So you have actually two variables there. You have t, the time, since you have plucked the string, and then you have x, your position along the string. So the height of the string would vary at different places and also at different times. So that's actually what's called a partial differential equation, because it has multiple independent variables. So in this video, I just want to give you a feel for ordinary differential equations, which involve just a single independent variable. So let's switch over to the document camera now that Sophie has gotten in position for her mid-afternoon nap, and we'll do a few examples. So I know a few of you have taken a course in differential equations already, and I know some of you haven't. So the good news is that the basics aren't all that difficult to understand. So many physical situations that we encounter can be described by relating rates of change. Okay, a very well-known one is one of Newton's laws. It says force equals mass times acceleration. And we know from calculus that acceleration is a derivative. Acceleration is change in velocity, and that is itself a derivative. Velocity is change in position. So you could say that is a second order differential equation. So it says that the force is equal to the mass times the second derivative of this function. Okay, and there are lots of other physical situations where the rate of change comes into play to describing what's going on. And we'll talk about a couple of those. Now, you solve a differential equation by finding a function that satisfies the differential equation, and also something called the initial condition. So a simple example might be the situation of population growth. Now, it's a common kind of starting assumption here that the rate of change in the population, that's what I've got over here, derivative of population with respect to time, is proportional to the size of the population at any given time. So in other words, change in population with respect to time is equal to a scalar multiple of the size of the population. Now, a differential equation like this can be solved with a technique called separation of variables. So, as you can see, we have two variables, p for population and t for time, and in this case, separation of variables means hopefully just what you think it means. What we're going to do is we're going to get everything that has a variable p over to one side and everything that doesn't over to the other side. So we'll just do this, and so that's the separation. And now we will integrate both sides of this. Okay, now here we're integrating a constant with respect to t. Kt plus c, that's what I get over here. Now over here, I'm integrating the function 1 over p. Okay, perhaps for clarity, I'll rewrite it like this. And we remember from our calculus, you integrate 1 over something, you get ln. Alright, now I don't need to worry about a plus c on this side too, because I already have one over here. Alright, now I want an expression for p as a function of t. In other words, I want to write p equals, and then over here I want to have an expression that depends only on t. Over here I've got ln of p, and to kind of get rid of the ln, I'm going to use the exponential function. So if I do that over here, I'll have this. Now, I'm using, oops, sorry, couldn't see that. I'm using some rules for exponents down here. Okay, now it's typically written, it typically isn't written as e to the c anymore. E to the constant, well, that's still a constant. And it turns out, in fact, that that is the initial population. So we usually call that P0 for initial population. And that, of course, is because if you plug in t equals 0, this portion would be a 1, and you'd be left with whatever this is. So when t equals 0, this factor determines the value that you're going to get. Okay? So that is how we can use separation of variables to solve this differential equation. Just some general notes over here on the side. K is the growth rate. Okay, so in other words, the constant of proportionality that we had way back up here is the growth rate. Okay, so let's do an actual concrete example of this. Okay, so here we've got our example. So we're going to suppose that the population of the Earth was about 3 billion in 1970, and the growth rate was 2% per year. And we're going to try to answer the question, when will the population reach 20 billion? Okay, so let me just talk a little bit about the strategy that I'll be using here. I'm going to find a function for the population, and that function will depend on the variable t for time. And then once I've got that function, I'm going to solve an equation. And I'm going to solve an algebraic equation to get the t value that I'm looking for. Okay, so this is our differential equation. Change in population with respect to time is equal to 0.02 times the current population. Okay, that's what this sentence right here is saying. The growth rate is 2% per year. So that means the change in the population with respect to time is equal to 2% of the population at that time. And also, the initial population equals 3, and of course we're measuring in billions. That 3 stands for 3 billion. And of course I'm setting t equals 0 to 1970. That kind of fits the situation that we have right there. Okay, so using our separation of variables technique, we're going to get the p's together on one side, and then everything that doesn't have a p will go to the other side. So we'll divide this p over, multiply both sides by dt, and get this. And as we saw last time, this leads to a situation like this. And here we know data for the initial condition. Okay, so this is the function that gives us our population at any time t. And now what we're going to do is solve an equation. The question asked us when the population of the Earth is going to be 20 billion. So we're going to get an algebraic equation with t as our unknown. Okay, now you got an exponential equation. You need to think back to your algebra. You want to solve an exponential equation, you need to use logs. So, I'm going to get the exponential function by itself. I'm going to convert this to a logarithmic equation, because we remember that every exponential equation is equivalent to a log equation. And of course ln stands for log base e. The reason I'm using ln here is because my exponential function was base e. So I can get the value of t by taking ln of 20 over 3, whatever that is. And then once I get that answer, I'll divide by, once I get that answer, I will divide by 0.02. Okay, so at this stage, I'll need to get out my calculator and calculate. So, there's some glare. Okay, so ln of 20 over 3, compute that, and then divide the answer by 0.02. Okay, so this calculator is telling me that it's approximately 90, it's almost 95 years. So t is approximately 95. Now remember, t equals 0 corresponds to the year 1970. So we're talking about 95 years after 1970. So that'd be 2065. So that is a quick example of a fairly simple situation that uses a differential equation to model something that we're seeing in the physical world. There are many other situations where a physical situation can be modeled very easily by a differential equation. One such situation is heating and cooling. So our next video, which we'll put a link to right down there, will be a kind of differential equation that models the temperature of an object. And in fact, there's really, you could do a whole course on differential equations. In fact, most universities do that. In fact, you could do multiple courses. You could do ordinary differential equations and partial differential equations and numerical differential equations. So that's 3 courses right there just on this one subject. So remember that kind of all that flurry of activity goes back to this period that we're talking about. So right after Euler made all of his work, did all of his voluminous contributions. We have about 100-year period of growth of the applications of calculus, and differential equations is one of the main areas where we see all this activity right now. And we'll continue with chapter 13 in that next video.